All right, it's good to see that all the tensor discussion last time didn't scare everyone away. But I did want to start back with that and clarify a few things before we get back in line with where we're going with the rest of the course. So for the D33 and similar sorts of notation, I just want to make sure that everybody's on the same page with how this works. So as an example, I've got here a picture of a slab, a rectangle of some sort of a piezoelectric. And so we have applied an electric field to it and pulled that material. So that's what the arrows are meant to represent. So by pulling it, it's no longer completely random. Now we have a defined three direction, and that three direction is determined by the direction that we pull the material. That's convention. We're going to start with that. So in order to do that, let's say we would have put electrodes on the top and bottom, applied an electric field, and gotten the material to pull. So now that we have that that lower symmetry, we've broken symmetry and now have a defined three direction. When we talk about a D33 or a D31, that's relative to that three direction. So D33 means that we apply an electric field in that three direction, and we also get a strain in that three direction. Or it means that we apply the strain in the three direction, and what we're measuring is the charge buildup in that three direction. So that's what this refers to, is if we're applying the field or applying the strain in the same direction as polling and making the measurement of the other one in that same direction as polling. So alternatively, and we talked about Poisson's ratio last time, when we do that, let's say we apply a field in the three direction, we're going to get strain in that three direction. We're also going to get a shrinkage laterally. That's the one direction. It's actually one direction and two direction. So this would be two, that's one. Again, just by convention. Those are going to happen whether we like it or not. So whether we measure the D33 or the D31, when we apply a field along three, we get strain in both three and one. That's what these coefficients are referring to. And so the way that I drew it on here, I basically fixed the bottom and had the entire strain sort of growing up from that. But then I also wanted to show that you're getting lateral in both directions. And so and in the two direction back here, I just showed it as one. So hopefully that doesn't confuse people, but I wanted to clarify what the three and the one and two and all these mean for starting off with a completely random material. By polling it, you are introducing that three direction. So if you want to take advantage of this lateral dimension, for example, you still apply a field here and get a change in dimensions laterally. That's what the D31, D32, that's what those refer to. All right, so I guess one other piece on that I should point out. Let's say that we have an example where we have the same sort of setup, but now it's a thin film on top of a rigid substrate. If we apply that same electric field through the thickness, we're going to get a change in dimensions laterally. What's that going to do? It's going to cause it to bend. So you can take advantage of that D31 coefficient to get large out of plane strains via bending if you're dealing with a material on a substrate, for example. So that doesn't necessarily have to be a thin film. You can do the same thing with little blocks of piezos on top of a larger membrane, or a lot of different options like that. But it's a mechanism for increasing that strain, because while I've drawn the D33 relatively large on here from a cartoon perspective, keep in mind that most of these coefficients are in the picometers per volt. So that's really, really tiny direct strain, but the force is very large. So you can bend other things around it and enhance that enhance that level of strain if that's what you're after. So any questions on that, please let me know. I will update the slides that are on Dropbox with these new cartoons so that hopefully you can use those as a reference if you need to go back to them. But any questions, just please ask. So also along those lines, we talked about D15 before. So that would be an example where you start off with this material. Let's say you put the electrodes on the top and bottom and hold the material along 3, just like is shown in this cartoon. But now we go back, and after we've pulled the material, now we want to add electrodes to the sides. So let's put an electrode here and an electrode on the opposite, the corresponding side. So that would be the one direction. Now that it's pulled along 3, D15 means that we can then apply electrode on the side and get it to shear. So you can get the whole thing to lean over. So again, that's one possible way of increasing the magnitude of the strain responses if you have that shear with something else sticking on top of it, a static piece or of some sort. So hopefully that clarifies the nomenclature. We will happy to come back to this if people are interested, but just wanted to clarify that before we move on. Okay, so as a reminder, we're applying an electric field to these ferroelectric materials, getting all the domains to line up, and then taking advantage of that for the piezo applications. So last time we ended with talking about how quickly this happens. So we have a nucleation and growth sort of process where we apply field, and the domains that are oriented along the direction of that field grow at the expense of the domains that are oriented in a different direction. And so we talked about the impact of that on the kinetics. So the energy that's involved is part of it, and then the way that the domain walls are moving is another part that determines how quickly this happens. And so from that, I want to get into the frequency dependence aspect of it. So if there's one thing that I can convey to you in the course of this class about this simplest way to get really useful information about your material, it doesn't matter what the material is. If you care about its electrical behavior, measure it as a function of frequency. Measure the conductivity as a function of frequency, measure resistivity, whatever it is, the ferroelectric hysteresis loop, the piezo response, it doesn't matter. Measure it as a function of frequency, and you can understand a lot of useful information about what's really happening in the underlying material and behavior. So this is just one simple example. So last time I showed you a little bit about Mertz's law and how as we apply a field, the polarization is going to maximize, and the harder you push it, so the larger the field you apply, the faster that happens. So this is an example on the top from Simon Fichtner's group at the University of Kiel, doing these kinds of measurements on aluminum scandium nitride ferroelectrics when they're first developed. So this is the year after Simon's group showed the rest of the world that aluminum scandium nitride could be ferroelectric in the first place. And they're already doing kinetic experiments on how fast those domain walls can move. And you'll see here that as you increase the voltage that's applied, the electric field, you can make that polarization transition from pointing down to pointing up or vice versa happen faster and faster and faster. And we talked last time about using the KAI model, the Ishibashi's KAI model to describe that the frequency dependence, this time dependence of the nucleation growth process. So you can see the same sorts of things with other materials there on the bottom. These kinds of measurements are a little more, they're not quite as simple as they look, because it's really easy to get artifacts from your measurement or apparatus if you're going really, really fast. But what I want you to take away from it is, now let's stop and think about what this kind of scenario would look like for just a hysteresis loop. So I've got standard polarization versus field hysteresis loop for any miscellaneous ferroelectric. It doesn't have to be this aluminum scandium nitride stuff. How would this polarization versus field hysteresis loop look different for different measurement frequencies? And what does that tell us about what is happening inside the material? So if everything is absolutely perfect, there are no loss mechanisms, it's just how the frequency dependence is dominated entirely by how quickly those domain walls can nucleate and grow, then if I start off with a baseline hysteresis loop that looks something like that, and again, I'll apologize for my poor artistry. If this is our baseline and everything is dominated by the intrinsic response of the material, so this is just how quickly the domain walls are moving. If I go faster and faster, so a higher frequency, what's that going to look like? Higher frequency means I have to actually push the material harder to get it to switch. So you'll notice there's no time axis on this polarization versus field hysteresis loop. There's no time axis on there, but we can understand what's going on by making these measurements at different frequencies. So let's say I go at a higher frequency, it's going to have a little bit higher coercive field because I have to push it harder to get it to switch. And if I go at another frequency, even faster, it's going to be a little bit higher. Might even get to the point where I'm not fully able to saturate it. So maybe the total polarization doesn't quite get as high as it does at lower fields because they just don't give it enough time to fully saturate. So in this example, this would be going from, so that's increasing measurement frequency. So as we increase the frequency, the apparent coercive field is going to grow. I say apparent coercive field. So that is a reminder that the coercive field itself is not an intrinsic value. It depends on the measurement conditions. It depends on the frequency of the measurement, among other things. And so just redoing the measurement at a series of different frequencies can tell you a lot about what's actually happening in the material. So let's try again with another example. We have the same polarization versus field. And now instead of having a perfect material, I'm going to talk about one that has some loss involved. So there are a handful of free carriers that are around that if I apply a DC bias, this looks like it's got a reasonably high conductivity. So it's kind of leaky. So I'm going to again start with a baseline hysteresis loop. Sorry for that. The loop down here, that shouldn't exist. Actually, I'm just going to redo that. Right, I apologize. My iPad and the screen are not keeping up with each other. So we'll try one last time. In worst case, you're just going to have to live with an imperfect loop. Okay, so this is our baseline. If this material is leaky, now I'm going to go down in frequency this time. So if this is our baseline, kind of happy, perfect looking material, if this is a sample that conducts a little bit of charge when I apply field to it, as I reduce the measurement frequency, more of this polarization contribution is actually going to come from that conductivity. And so it's going to sort of bloat out and it looks like the polarization actually got larger. And it looks like the coercive field got larger. And then if I go to an even lower frequency, it's going to turn into a balloon. So this would be a case where we're actually going down in frequency for a lossy sample. So if you want to know what's going on in your material, make measurements at different measurement frequencies, and it can help tell you a lot. So you'll notice on that lossy example, both the coercive field got larger and the apparent polarization got larger because the measurement instrument doesn't know what it's measuring. It's just measuring charge. You apply a field, it measures charge, and whether that charge comes from the actual switching of the ferroelectric or from just leakage so conductivity, the instrument doesn't know the difference. They're the same electrons. So being able to measure as a function of frequency and seeing how the coercive field and the polarization respond can help a lot. So again, if you have a very low loss, sort of perfect material, the coercive field and Reaumur polarization should be very similar for different frequencies, but the coercive field will gradually get fatter and fatter as you go faster because it takes time for those domain walls to move through the sample. At some point, you're going to be measuring so fast that it can't keep up at all, or you could go so slowly that you won't see any difference at all in the measurement because you're not limited by the sample itself. Can you determine how much of the apparent polarization is due to loss? Great question. Yes. So it's difficult to quantitatively do that just from these polarization versus hysteresis loops, although some people try to do that. It's hard to do it quantitatively. So I'll give you two answers to that. The first thing is the super simple one that just tells you whether or not you need to do the more quantitative one. And the first thing that I do is to just make a series of nested loops at either at different frequencies or at different maximum voltages. So you can measure the exact same frequency, but just go to a higher maximum voltage each time. And if the coercive fields and Reaumur polarization values line up fairly well as you increase the voltage and or change the measurement frequency, that's a really good indication that what you're measuring is the actual domain response of the material and not being dominated by loss. If you change the frequency and or change the maximum measurement field and the loops get really bloaty and so instead of having a nice sharp point out here, if it does this, so think about what that would mean. If you're applying a field, so you're applying an electric field, you're going up in field, and you get to a maximum, and then you turn around and start removing the field, and the apparent polarization is still going up. The only way that can happen is if there's current flowing and essentially there's momentum. So it's really inductance, but there's essentially momentum from all that charge flowing that is causing the apparent polarization. So the charges that the circuit is measuring continue to increase, even though you're decreasing the field now. That is a really good indication that there's some loss mechanisms that are happening. If you get a nice sharp point up here that's fully saturated, that's a strong indication that you're not dominated by leakage. So that's the quick and easy, non-quantitative, but still very helpful approach. The other, if you'll remember when we talked about Mertz's law, the very first plot that I showed that if you apply voltage as a function of time, that in a non-switching pulse, you get a just capacitive peak. And in a switching pulse, you get that same, and then there will be a bunch of current. Sorry, this is you're actually measuring the current there, not the voltage. You're applying a voltage, measuring the current. There we go. So you can take advantage of that by just making that same measurement in the same polarity a couple of different times. So the very first time that you apply, let's say you have a material that's pulled this direction, and you apply a voltage that is going to want to switch the polarization down. So that very first time that you apply a voltage to it, you're going to see something like that behavior where you see a large current pulse. The second time, now the sample is pulled down. And if you apply another voltage pulse that's in the same direction as the one you just applied, there's nothing left to switch. So that means the first time you apply a voltage pulse, so let's do voltage here, current down here, you'll see a peak and then the switching. And then the second time you apply a voltage pulse, you'll see just the non-switching component. And then you could do another voltage pulse again if you wanted to, and it would be non-switching. So if you wanted to, then you could switch it around again and now apply a voltage in the other direction. And what's that going to look like? We're going to see a current and then a switching current that's associated with that. And so the way that is generally referred to in the literature is PUND. It's positive, up, negative, down. So that means you're applying a positive pulse, and then the U is in the same direction. So that's basically what this would be, the P pulse. This would be the U pulse. In the way that I've drawn it, this would be a second U pulse. You usually don't bother with that. This one would be the negative pulse, and then you could follow that with another negative pulse, which would be the D. And so from that, you can make a series of multiple pulses in the same direction. The first one will switch it, the second one won't switch it. So that allows you to quantitatively back out how much of the current that you're seeing, how much of the charge that you're seeing is from switching, and how much is just from either leakage or charging the capacitor, or both. It's never quite as simple as this, because maybe you only switched 90% of your sample that very first time, and then you get 10% of the sample switching the second time. But it can be a really helpful tool for helping you figure out maybe you need to know why you're not switching all 100% of your sample, and that tells you that you've got a lot of defects that are piled up, or you've got some other strain effects, or these kinds of things. So yeah, those are really helpful techniques. So hopefully the concept of frequency dependence of the hysteresis loops makes sense now. You'll see the same kind of thing in the strain response. So let's look at what a hysteresis loop for a piezoelectric actually looks like for strain. So instead of me trying to draw this and failing miserably like you just saw, I've stolen some images here. These are from PI Piezo Products. So that's a commercial supplier of piezoelectrics. Great looking loops on here. What they're showing is, as we talked about before, when you start off with a completely virgin sample, the first time you pull it, then you end up in this hysteresis loop, and you can cycle around that as many times as you want. You'll also notice what I was just talking about. You can do, once you're already pulled, you can do unipolar pulses this way. And if you go backwards just a little bit, then you may enhance that back switching and end up with what is known as a minor loop. So this is indicative of a little bit of switching, but not the whole thing. So that's another way that you can see what's happening within your sample. So the loop on the right here is what you're used to seeing for ferroelectric hysteresis loops. The one on the left is actually the strain loop for the same sort of measurement. So this is strain as a function of electric field. And now we're starting here at zero strain. And the strain, actually, this is true for both the polarization and strain. So how do you know what zero is? If you're the instrument making the measurement, there is no built-in zero polarization. All you're ever able to measure in these scenarios is a change in charge or a change in strain, because the instrument has no idea where you started. So when these measurements are made on commercial, so the Radiant system from Albuquerque, the Exact system from Germany, they will, by default, and you can change this if you want to, but by default, they will assume that you're starting with an unpulled sample, and they will run all the way through a full hysteresis loop, and then do a second measurement. So let me redo that. So it assumes you're starting at zero, applies a full loop, comes back to zero. And then it says, all right, now I'm going to assume that I'm starting here. So when I make the second measurement, then I'm going to be able to measure whatever value I'm measuring for the charge is actually twice the remnant polarization, because I'm going from the completely negative to completely positive version. And then it just says, here's the total amount I measured. I divide it in half. I'm going to set that as my zero, and then I plot it. So by default, that's the way the commercial systems measure these hysteresis loops. It actually, what it plots, what it shows you the first time you hit the button is actually the second loop that it made, because it makes the first one to pull it, and then the second one to quantify from there. the same concept applies for strain. So the very first time you start with a virgin sample, the first time you apply an electric field, what is zero strain? It's arbitrary because everything is relative. So strain is a change. So in this case, we're going to apply this field, and eventually when the material starts to pull, so this initial decrease here is this very low slope portion right there. And then as the domain walls are starting to flip, we are getting more and more and more strain. So that's this increase in strain as we continue to apply electric field. And as it saturates, then this bends over and we get less and less strain. It doesn't quite go to zero. It doesn't get completely flat, just like the polarization field loop doesn't get completely flat. So that's an important concept. The slope of these lines, the slope here, it's dP, dE. You've seen that before. That is just relative permittivity. So the slope of the hysteresis loop at any point, the local slope is the relative permittivity at that point. What would that be for the slope over here? So the slope of d-strain, we'll use a capital S because that's what's shown on here, d field. What's the change in strain with field? That's just the d coefficient. So the local slopes of these hysteresis loops are really, really important because that tells you how each one of these more intrinsic values is going to change as we change field. All right, so with the strain loop, we started here at 0. We started switching a whole bunch of these domain walls. It starts to saturate, and now we stop and remove the field. So now we remove the field, and it's going to relax. And those, because of the stresses that are built up, that material relaxes and comes back to some amount of remnant strain. So that remnant strain is completely analogous to the remnant polarization that is in the ferroelectric hysteresis loop. So now on the ferroelectric side, we're going to continue, we're going to start applying a field in the opposite direction. So now instead of removing the positive, now we're adding a negative field. So on the strain side, it continues down this direction. So you'll see now we're increasing the magnitude of the field, but it's opposite the direction of the poling, and the material is actually shrinking. So we are now applying a field opposite. So if all of our domains are pointing this direction, now we're applying a small enough field in the other, we're applying a little bit of a field in the other direction, and which is making the sample actually shrink. So that's what's happening in this portion. And eventually we get to this basin, and that is the coercive field. So the minimum in the total strain is right here, where we're now pushing against the poling of the material enough that suddenly it starts to switch after all. And so now we're actually switching the polarization of the material. And as we flip the direction of these dipoles, now the additional strain that we add is going to make it continue to grow again. So when we apply a field in the direction of the poling, the material is going to get bigger. When we apply the direction of the field opposite poling, it shrinks. And when we get to the coercive field, that's when we flip the direction of that polarization. And so you're going to flip the response of the material relative to the amount of field that you're applying. So that sounds weird, right? I've started here at the remnant polarization. Started here at the remnant polarization. I don't have any field on the material at all, but I do know that it's pulled. Let's say that it's pulled up, and I'm applying a field opposite that. It shrinks. And now I keep increasing the amount of field that I apply, and suddenly the material stops shrinking and starts growing again. And that is my indication that I have flipped the polarization because I've gone through this coercive field. Hopefully that makes sense. If you're drawing these hysteresis loops, or if you're measuring something, so that's why you end up with this butterfly approach. So you can probably imagine that if you're operating this in an application, you probably don't want to go through that kind of a transition over and over again, because that's going to be really hard to control what your sample is actually doing. So most of the time, for most applications, people will be operating in this region. So you stay away from the coercive field because you don't necessarily want to switch a bunch of stuff during the operation of your sample. You might be operating fully saturated, but because remember the local slope is the D coefficient, operating up here is actually a lower piezoelectric response than operating down here. So that corresponds to this portion of the hysteresis loop on the ferroelectric side. All right, any questions on strain field hysteresis loops? Happy to go into more information on those. We will next week get into a little bit more information about what's going on here as the material saturates. For now, just remember that a lot of the large strain that you're seeing here is from domain wall motion. So you're switching 90-degree domain walls, and as you flip something from here to there, there's a large amount of strain that's associated with it. So that's where you get these really large strains. But because of that large strain, you're potentially damaging your material as well. So a lot of times you want to avoid that hysteretic response and just operate in the closer to linear regime because that's easier to control. All right, so now we get to talk about PZT. And PZT is the example that we're going to use for a lot of these. It's the example material that we're going to use for a lot of these because it is the classic. It's still the king, even though people have been trying to get rid of lead in a lot of these piezoelectric materials for decades. And later on, we will give some examples of lead-free piezoelectrics that are approaching the performance of PZT, but PZT is still the prototype. It's still the dominant market leader from a material perspective. So we will use it as an example. It is not the only piezoelectric out there, obviously, but it's a good place to start. So if we're looking at the phase diagram of PZT, so this is the subsolidus phase diagram. Everything that's on here is solid. So the melting point is much higher in temperature than we're looking at here. So this is lead, zirconium, titanium. So on this end, we have lead titanate. And on this end, we have lead zirconate. And on the lead titanate, so lead titanate itself is fully tetragonal. Lead zirconate is actually by itself orthorhombic, but with just not too much titanium added in. So titanium and zirconium are both 4+. They form a nice, convenient solid solution. You can replace them with the other fairly easily. If we add just a little bit of titanium, then the material becomes rhombohedral. And in all cases, this still has the perovskite crystal structure. So we still have the exact same overall structure, but we're changing the symmetry a little bit. So the symmetry of the material at sufficiently high temperatures is cubic, just like we saw with barium titanate. At high temperatures, the prototype symmetry is cubic. And then as we cool down, if we're lead titanate rich, titanium rich, then it turns into a tetragonal form. And if it's zirconium rich, then it turns into a rhombohedral form. That's just the lowest energy state. So in between, there's a boundary in here. And that boundary is almost vertical. So it does have a little bit of curvature to it, but it's really close to being vertical. And so this is known as morphotropic phase boundary. And so this is the classic morphotropic phase boundary. It is not the only one, but to my knowledge, it is still the best example of being a phase boundary that is completely driven by composition, much more than by temperature. So a lot of times this is an example of a phase boundary that is largely driven by temperature, right? As you heat up a composition here, it goes from rhombohedral to cubic. As you heat up a composition here, it goes from tetragonal to cubic. But in the middle, this morphotropic phase boundary, as you change the composition, you change the symmetry of the material, and it almost doesn't matter what temperature you're sitting at, which one you end up with. So that's really handy if you want to make something that sits at this phase boundary, because we talked about with barium titanate and with multi-layer ceramic capacitors, that materials give you the best performance when they're frustrated. So when they're sitting right at a phase boundary, a lot of times you'll get the highest performance. This is a situation where we can lock in that frustration by sitting right at the phase boundary when we make the material based on the chemistry. And then we can operate it over a wide range of temperatures and it still give us that really high, high performance. And so that's the advantage of this morphotropic phase boundary, is that we can lock in that frustration chemically when we make the sample and then operate over a broad temperature range in it, and it still gives us good response. So the specific phase diagram that I've shown here was taken from Jaffe, Cook and Jaffe, and then I colored it in and cleaned it up a little bit. But it's old enough that it doesn't actually include a new feature that has been discovered in the last 10, 15, 20 years. There's a very thin region of monoclinic phase right there. And having that extra monoclinic phase in there is another reason that this that the PZT system gives so much better response at that morphotropic phase boundary, because now you don't just have two phases that are competing, you actually have three. And it was a really tricky thing to find that, because people have been making PZT for decades. And it wasn't until early 2000s that it was conclusively determined that there really was an additional phase in there. Basically comes down to it's the size of the probe that you're using to make the measurement, whether you're using X-ray diffraction or TEM or something in between, you can get different answers. And in getting all of those to agree with one another was more challenging than one might think. So the reason we care about that, we start with this morphotropic phase boundary, and if we lay on top of it any property we feel like, so in this case, I've stolen these plots from Jaffe, Cook and Jaffe again. On here, we've got relative permittivity. Over here, we've got the coupling coefficient. You could do this for just about any property that you want to, and it maximizes right at that morphotropic phase boundary. So the exact composition is shifted a little bit because the graphics weren't perfect, but basically right on top of the phase boundary, you get a 5x, 10x, 20x improvement in whatever property you're looking for. Relative permittivity, coupling coefficient, piezoelectric response, doesn't really matter what it is. The response is enhanced at that phase boundary because the hand wavy answer is because the material is frustrated and therefore it's going to be more responsive to whatever your external stimulus is. A bit more quantitative version of that is that if you look at the possible polar directions, so we talked way back when we were talking about symmetry, about when we go from cubic to tetragonal, now we have a polar direction along what is now the long axis, the c-axis. That c-axis can be pointing in any of three directions. So it could be along A, B, or C. The long axis defines that being C, but there's no reason that you can't have a c-axis laying down in this direction or that direction. So that means that in a tetragonal unit cell, and it can also be either pointing one direction or the other. So that means for a given cube, you stretch it into tetragonal. Now you have 6 potential polar directions. And if you want to take advantage of that polarity by getting ferroelectric switching, or even at the other direction, when we talked about the direction dependent relative permittivity, you get much higher permittivity when it's along 100, right? Whichever direction you want, now you have 6 options for the tetragonal crystal structure, for the tetragonal unit cell. In rhombohedral, because that polar direction is along the body diagonal, so that would be along these body diagonals, the 1, 1, 1 directions, Now you have 8 possibilities. In orthorhombic, so orthorhombic, remember, is a rectangle for which all 3 dimensions are a little bit different. So that means that the polar direction for rhombohedral, and I don't have a rhombohedral lattice parameter or pretend cube drawn on there, but that ends up being along the face center, the face diagonal. So that means that you have 12 possible directions for orthorhombic. What that means is, let's say you're sitting right here at the morphotropic phase boundary, and you apply an electric field. If you're right there at the phase boundary where the material can't quite decide if it wants to be rhombohedral or tetragonal, and from an energy perspective, adding that electric field can shift it just a little bit one way or the other. So maybe that just a tiny little electric field is enough to make this local region say, you know what, I would be tetragonal, but this is pushing me towards rhombohedral because the polar direction is 1, 1, 1, and this is pulling me in the 1, 1, 1 direction. Now, suddenly you have 6 plus 8. So at the boundary, you've got 14 different possible polar directions. And that's just locally, you might be able to shift the symmetry of the material a little bit, and take advantage of the higher performance in that along that direction. So that's the symmetry related reason for enhancement at those morphotropic phase boundaries. And so there are other ways of engineering improved response out of piezoelectrics and that kind of thing, but this feature right here and the massive performance gain that you can get out of PZT over just plain lead titanate or plain lead zirconate or barium titanate, this morphotropic phase boundary and its associated increase in properties is the reason that as people are trying to replace PZT or lead-based materials in general with non-lead options, many of them start by looking for morphotropic phase boundaries in other chemical systems to try and get the same kind of enhancement at that phase boundary. So it's harder than it looks. People have been working on it for 40 years so far and have made some progress for sure, but there's still a ways to go. So for example, KNN, potassium sodium niobate, there's been a lot of great developments there. The bismuth containing titanates also are looking really promising for lead-free replacements. So bismuth is nowhere near as hazardous as lead. In fact, it's in Pepto-Bismol, so it's not a huge health hazard, even though technically on the periodic table it does look like it's a heavy metal. It is a high Z metal. It's not a toxic one. The problem with all of these is that none of them really offer the flexibility yet. None of them yet offer the flexibility that PZT does. So the nice thing about PZT, and we talked about this a little bit earlier, and we're going to get into in more detail, is that by starting with this baseline PZT system and then doping it with different allovalent or different heterovalent dopants, so we can add donor dopants to make it softer, we can add acceptor dopants to make it harder. We can change its response over a huge variety. So we can get a very high piezoelectric response with a little bit of extra loss in a relatively small coercive field, or we can get a large coercive field and stiffer response. None of these other systems, and I should add modified barium titanate in there as well. So there's a lot of really good work on starting from barium titanate and doping it with a lot of different things to get increased piezo response. So far, each of these lead-free systems can do one of those classes of piezoelectric response really well. So for example, KNN as an example, you can make a very, very good high power hard piezoelectric out of KNN. It's so far been much, much more challenging to get a soft KNN that gives you the kind of very high piezoelectric response that you can get out of soft PZT. However, KNN and some of the BNKT samples as well, they actually can end up performing better than PZT, than all of the flavors of PZT at really high drive powers. And so that's something to keep in mind. We're finally at the point where there are alternatives to PZT that have better performance. They just happen to be very application specific. Yeah, Eric, you have a question? Guess not.
Oh, no.
All right. So let's see what we can do about doping PZT. So again, this is going to use PCT as an example, and I'm stealing some classic literature from Jaffe again. And this year, in Jaffe's book, he was pulling it from a lot of other primary literature. So if you want the originals, you can go back to those. What I like about this plot, it's combining a lot of different data into one spot, and I'll zoom in on this top portion. So this is the same plot. We're just zooming in on so you can see a little bit better what materials we're looking at. And so if you take all of these examples together, you'll see there are basically two different categories. There's the baseline PCT, which is undoped, or in other words, not intentionally doped. So that means there's some impurity in there. They don't really know what the impurities are. They didn't put it there intentionally. But you'll notice that that is very similar to the acceptor dopants. The scandium is the one that's listed here. But acceptor dopants and unintentionally doped material, they're all down here in terms of resistivity as a function of 1/T here for Arrhenius. That's how you get semi-linear. The other category up here, there's a whole bunch of alphabet soup. It doesn't really matter which one of these donor dopants you put in there, but they all end up giving you very large increase in resistivity. So at a given temperature, you can get 3, 4, 5 orders of magnitude increase in resistivity by adding a donor dopant. So that means you're putting in something that has an extra electron and you're making the sample more resistive. So it's less conductive by a very large amount. So what does that tell us about what's going on? We get to go back to defect chemistry all over again. And really what it's telling us is that when we thought that we were starting with our baseline perfect material that was undoped, it probably wasn't perfect and undoped. And so adding these donors is compensating for whatever other defects are there. And the fact that it doesn't really matter which donor we put in, or honestly, how much of it. There's a lot of variation in values there. So you'll notice semiconductor people will talk in terms of donor doping in the parts per million or less. Ceramists, we like to deal in scooping things out of a bucket and throwing it into a large batch. So we're talking about percents. So this is a massive amount of doping. We're throwing a huge number of extra electrons into the sample, essentially, and still getting similar response. So what does that mean in terms of the behavior of the baseline material itself? To summarize what I was just scribbling on there, donor dopants increase resistivity, so that makes it a better insulator. In general, acceptor dopants decrease resistivity by a small amount, but nowhere near the same level. So that suggests that the baseline undoped material already has some acceptors around of some sort. So what might that be? So back to defect chemistry. So lead's volatile. You probably already know that in some way. If we're losing lead, so a lead vacancy is essentially an acceptor dopant. So if you put a 0 on a 2+, that's the same as putting a 3+ on a 4+, essentially, times 2. And so those lead vacancies can either be compensated by oxygen vacancies and or by electron holes. So lead, the fact that we are sintering these samples at high temperature and lead oxide are volatile, that means that we're probably nowhere near stoichiometric when we're making these things. So if you do end up with holes, they're going to increase conduction. If you have oxygen vacancies, those oxygen vacancies and lead vacancies combined, they're going to want to hang out together. So remember, at the sintering temperature, we are, the very fact that it is sintering means that there's enough thermal energy around for diffusion to happen. And so if things are able to diffuse, then the atoms are going to be able to rearrange themselves to some degree to be in a lowest energy state. And if you've got a effectively negatively charged lead vacancy and an effective positively charged oxygen vacancy, the overall system is going to be lower energy if those are somewhat near each other. So they might be immediately next to each other. There might be a couple of atom hops away, but they're going to want to cluster. And then we cool that sample back down. And suddenly there's not that much thermal energy around anymore. But those defects are still there. They've essentially been quenched in. And they were aligned with one another. They were not necessarily aligned. They were near each other to start with, and then you cool them down. And now you have built in this tiny little defect dipole. Because what is a dipole? It's just a charge separation. And so if you have an effective positive charge center and an effective negative charge center, you have a dipole, a defect dipole in this case. The same thing can happen if you have a scandium sitting on a titanium site, or any of the other acceptor dopants that they were listed on that last one. You could do the same thing with sodium on the lead site, so a 1+ on a 2+ site, these kinds of things. So you create these defect dipoles, and what the cartoon on the right is trying to show is that we already know that we are going to have these macroscopic domains, that the macroscopic polarization is going to be represented by these big black arrows for each domain. But within each domain, we're going to have these little bitty defect dipoles. They're going to be somewhat aligned. They don't necessarily have to be perfectly aligned, but they're going to be crystallographically in the same direction, and then it's going to be lower energy for them to be aligned with the direction of that domain. But now, because these little little white representations of those defect dipoles, because those are basically baked into the ionic vacancies, they're going to be hard to move, because moving those actually requires a diffusion of vacancies that hop together. Flipping this dipole of a domain, so moving a domain wall, you're just shifting this ion up and down a little bit. You're getting slightly off-center shift of the ions. They're not actually having to hop full lattice spaces or anything along those lines. Because these built-in defect dipoles are based around the ionic vacancies, or in another case, an actual 3+ ion on a 4+ side or something like that, they're going to be much, much harder to move around, because it requires things actually hopping a full lattice position. And because of that, they end up pinning the domain walls. So what that basically means is that it makes the domains harder to switch. So you apply an electric field and the domain wall starts to move, but then it runs into one of these defect dipoles, and that creates an energy barrier to continuing to move the domain wall. And when you have a bunch of pinning sites, you can actually end up with these kind of pinched loops. And yes, it looks a little bit like anti-ferroelectricity. We're actually going to cover anti-ferroelectricity next week. But in this case, that response is not because of true anti-ferroelectric structural setup. It is because of a bunch of very highly pinned domain walls. And the reason that it finally switches is you get to a high enough field, you can actually drive those these ionic defects to actually hop and move around and get real diffusion of at least a couple of lattice parameters. And so if you have these kinds of defect dipoles built in, that gives you an additional way of engineering how the material is going to respond under field. So it can be a good thing, it can be a bad thing. They're going to be there. So you just need to know how to deal with it. So how this manifests is that if we intentionally add more of these defect dipoles, then the material ends up being hard. And that hard refers to, well, for one, it actually does have a larger elastic modulus. But what it really means is that it has a larger coercive field. So it's harder to pull. You have to apply a larger electric field to get those dipoles to align, because you had all those little defect dipoles along the way that had to switch. And because you have to push on it a little bit harder, that means you end up with a steeper, generally, a steeper slope on your hysteresis loop. You'll also notice once it's saturated, you have a lower relative permittivity up here than in the soft material. So the soft material the easiest way to get a soft material in the PZT system is to donor dope it. So you can add lanthanum on the lead site. You can add niobium on the B site, the zirconium or titanium. And what that does is it compensates for it, eliminates those defect dipoles. And by not having those defect dipoles in the way, it makes the domain walls much easier to move around. And so you may recognize the shape of this hysteresis loop looks a lot like the prototype barium titanate hysteresis loop that I've been using as an example all the way through. And that's because this is one where you've got high domain wall mobility, therefore a high relative permittivity. And so if you look at the local slope, at low field or at high field, you'll have a higher permittivity in the soft PZT. You'll also have a higher piezoelectric response. So the D33, all the D coefficients are going to be significantly higher for the soft material. So you might think, well, if the whole purpose of having a piezoelectric is I want to be able to convert between electrical and mechanical energy, that means I need a high D coefficient. That means why on earth would I ever want to make a hard PZT? I want a high D, therefore I'm going to donor dope everything and just leave it at that. Well, that's great, unless you want to actually operate at a field somewhere out here. So if you wanted to operate at a field in somewhere in this range for the soft PZT, you would be cycling around this entire loop over and over and over again. And the material will end up fatiguing and breaking. And all of the area within this loop, there's loss associated with that. So the soft PZTs, because the domain walls are moving a lot more, there's energy dissipation associated with that. So soft PZTs have higher D coefficients, but they also have higher losses. They have higher relative permittivity, but they also have higher 10 delta. So they're going to have generally have higher 10 delta and losses associated with that. So depending on the application, this gives you an opportunity to just change the composition of your material very slightly. So you can throw in a couple of % of a donor dopant or a couple of % of an acceptor dopant and change from the baseline PZT to hard PZT to soft PZT and shift that around. That simplicity, relative simplicity, is one of the big reasons that PZT continues to dominate the piezoelectric market. So if you want to operate at larger fields, so let's say high power applications where you want to operate at these larger coercive fields, then you need to go to a hard PZT so that you can operate in this region. So you'll have a little bit lower D coefficient, you'll have a little bit lower relative permittivity, but you can operate at larger fields and not have as big of a losses and not have to worry about the nonlinear response of switching the material around during operation and all that kind of stuff. So hopefully that gives you a little bit of a flavor for what we want to do by engineering the PZTs. Then you can also get into, as you can imagine, changing the defect chemistry, as we talked about way back in the second lecture, I think. Changing the defect chemistry also changes diffusion coefficients because you've changed the relative concentrations of oxygens versus cations and this kind of thing. So you'll also end up with different default grain sizes in each of these and different centering kinetics. And so tuning that to your specific material and your specific application and everything else is another opportunity to tweak those. But just keep in mind that every time you're doping the material, you're not just changing the behavior at room temperature, you're also changing the sintering behavior, or at least have the potential for changing the sintering behavior because of that, you're messing around with the defect concentrations. All right, any questions on that one? So we've now talked about how we can dope the PZT systems. So I mentioned for donor dopants, we'll often use lanthanum on lead site, niobium on the B site. Those are the most common ones. There are plenty of other options. For hard PZT, a lot of times that will be iron on the B site. You can also put a singly charged cation on the A site. So you could put sodium or potassium on the lead site. that's not as common because it's hard enough to deal with one volatile cation, lead, adding other volatile cations like sodium or potassium, or if you want to dope donor on the A site, you can throw in bismuth. That just complicates things even further. There may be other advantages along the way, but it makes the processing more difficult. All right, so that's super fast overview of doping PZT. So a quick reminder about this. So we talked a while ago, I guess the very end of the last talk and the beginning of this one about the kinetics of this switching process. And I mentioned that seeing how these samples and different materials respond to different frequencies can tell you a lot about what's happening inside of the grains and at the domain level. Now we're going to take another approach to doing the same kind of thing and understanding what's going on with the domain wall motion. So macroscopically, if we want to make something hard or make something soft, we can do that by doping. But how do we know how effective that's been, or if it's done homogeneously, or what else we need to do? So I'm going to talk a little bit about a way that we can probe this without going through the full hysteresis loop and learn a bit more about what's happening in the material. So as a quick reminder, I'm going to use the simple tetragonal example because it's the easiest to draw. But once we have a polar unit cell, in this case tetragonal, the lowest energy state is for the ion to be offset in either the positive or the negative direction. It doesn't really matter. And now we've got this energy barrier to flip back and forth. So the ion wants to be hanging out off center. In order to get it to move to the other energy well, or to even sit in the middle, you've got to get over this energy barrier in some way. That's the way we describe it at the individual unit cell level. We talked a little bit about what it looks like at the little bit larger domain scale. But what does this really mean when we think about the distance between the two? So the scale between the two. So in an absolutely perfect material, that this kind of energy well schematic would apply at the unit cell level all the way up to a perfect single crystal. But we know that there are always defects around. There's always another force of some sort. So it might be local strain, it might be defects, it might be who knows what. But there's always going to be some noise and variations locally. So when we actually look at that energy landscape from one unit cell to the next, to the next, to the next, from one domain wall to the next, to the next, from one grain to the next, to the next, there's always going to be some variation. And so instead of having a nice smooth parabola, we actually end up with noise there locally. And so if we zoom in, there's going to be a bit of noise within that parabola. And one way to think about that is to, again, zoom in at one individual atom or one individual domain wall, or you can do this at whichever scale you want. But the argument is the same, is that if you're sitting in this wall and you're applying electric fields and getting the domain wall or the individual atom to wiggle back and forth, if it always wants to go right back to the same energy well, you apply a field and let go, and you apply a field and let go, that's reversible. If, on the other hand, the where you are within this noisy energy landscape is such that you apply a field in one direction and it actually does hop over a barrier and land in a different well, then that's irreversible, because now to push the atom back into its original well, you have to go over a higher barrier because this distance is higher than that distance. And so if you think about this conceptually, you can gradually increase the amount of, so let's think here, this one would be reversible at very low fields. And then you apply a large enough field to get over that barrier, and suddenly it becomes irreversible. So you can gradually increase the amount of field that you're applying, the amount of energy that you're providing to the system, and get a statistical distribution of reversible versus irreversible contributions. And that tells you a little bit about the noise within the energy landscape and just how speed bumpy your road is as you're trying to move these domain walls around. So the way that we're going to look at this is, like I said before, we're just going to start with little electric field and gradually get bigger and bigger and bigger. And because I am not a good artist, I stole these plots from one of Jacob Jones's papers, just to show you what this looks like for plotting out the polarization versus field response for these minor loops. So what you're doing is you're applying a coercive field less than, sorry, you're applying an electric field less than the coercive field. So we are applying a field and then reversing it, applying a field and reversing it, and then gradually increasing the value of that. And you'll notice that there's some width here. That's telling you that something is moving within the sample. Maybe that's electrons, free electrons that are charge carriers that are just sloshing around, and that's loss. Maybe it's domain walls that are actually moving a little bit, just like we're seeing here. And so if this was completely reversible, that would be a perfectly straight line. The fact that there is some width to it means that there's some irreversible contribution. And so we can quantify all of that. And putting this all together is known as Rayleigh analysis. There's a lot of equations up here that are there for your reference. Nazanin Masirigar out of Penn State for her thesis, she's now at Georgia Tech, is where I took these. Dragan Damjanovic and Susan Troy McKinstry did a lot of the initial development on this technique. But the idea is that a reversible response is going to be completely linear. An irreversible response is going to have some sort of width to that, because you're going to be pushing the walls. You have to push them harder in one direction than in the other. And so you end up with a little bit of hysteresis, even at much, much lower fields than are required to see the macroscopic hysteresis loop. And so from this, you can get a better idea of what's happening very locally within your sample. And so this is a really powerful technique for seeing what kinds of defect complexes you have, how many losses, what kinds of losses you're going to have during operation, and all these kind of things. So it allows you to, it doesn't let you look at one individual domain wall sloshing about, moving back and forth, but it can give you a very good statistical distribution of what those local environments look like to the domain walls. And so from that, the earlier one was measuring permittivity. This is the exact same technique. On the right, this was measuring permittivity. So this is some work that John Alfield and I did at CNDIA. And then on the left is some more work from Jacob Jones measuring the piezoelectric response. And so the concept is exactly the same, whether you're measuring permittivity or strain. If you're measuring subcoercive field and just seeing how much contribution you're getting from domain walls and how much you're getting from just stretching of the ions, you can back out a little bit of information about that, the losses and the pinning sites and the distribution of those pinning sites and how easy it is to pull the material. So that's a super quick introduction to Rayleigh analysis. It can be a really deep tool. It can also be just a quick check and say, tell you a little bit about how your domain walls are moving and confirm or refute some of the other measurements that you get out of just making a hysteresis loop measurement. There are also other techniques like fork first order reversal curve measurement, PRESAC analysis that can get at similar kinds of things. I like Rayleigh because it is relatively simple and very powerful. All right, that's the last of the fundamentals from the piezoelectric and ferroelectric portion. So because so much of this was based around the crystallography and what is the direction of polling and what is the direction of the field when I'm operating and all that, I want you to think about how that applies to the materials that you're working on. So this is the crystallography about the way that the things are set up, and do I need additional do I need to break symmetry to get the performance that I want, and how can I do that? And then similarly, because we were just talking about a lot of the dynamic responses, how much does the behavior of your product vary from microseconds to milliseconds to years? And is that something that you have thought about, need to think about? All right, so again, as always, don't feel obligated to send that to me, but I'm happy to offer feedback if you want to. I just want you to think about it from that perspective. All right. So now we get to jump into coupled properties. And so this is another one of my favorite topics because we get to talk about the Heckman diagram. And this is a reminder that we always break material properties up and talk about, I'm going to apply an electric field here. I'm going to apply a strain there. I'm going to change the temperature here as if they're independent, but they're not. Boundary conditions always matter. And sometimes those can come back to bite you. If you don't think about them, sometimes they can be very helpful. And so we're going to jump into the beginnings of this and then we'll wrap it up next week. But I want to get into why this is the case and what it really means. So
Jeff, can I ask you a question first?
please.
So this is about the domain walls and how they change during polling and how they grow. So last lecture you talked about modeling this with JMAC kinetics. How would you observe that domain growth experimentally?
Great question. It depends on your sample. So the classic example from Mertz back in the 50s and 60s, he was using barium titanate single crystals and looking at it optically. And so because the index of refraction varies with crystallographic orientation, you can actually see the domain walls optically. Well, you can see the domains optically because you're getting scattered at the boundaries. That same technique works for PMNPT single crystals. It works for lithium tantalate single crystals, lithium niobate. There are a lot of people that have done fundamental work using optical scattering and domain walls from those kinds of systems. If you're not lucky enough to have a single crystal, that's a bit harder. So one option, there are a handful of studies of actually watching those domain walls move in a TEM or in an SEM. So you can, because you get contrast at the domain walls, either from channeling in the electron beam or again, because of the orientation, or you can see them move a little bit strain wise. You can use PFM, so piezo force microscopy, piezo response force microscopy. Those are the most common techniques. So doing in situ measurements along those lines. If by C you're okay with statistical representations, then that's why I came back to this slide. Jacob Jones and John Daniels at UNSW in Australia and Dragon at EPFL and a lot of other people have done a lot of great work on watching domain wall response in front of an X-ray beam. And so that doesn't mean you get to see it with your eyes, but you can see the results and watch different peaks splitting and moving around and those kinds of things and back things out statistically. So it depends on what your sample looks like, what you're trying to measure, and what you mean by C. So I don't know if that actually helped at all, but there are a bunch of different ways that you can go about it.
Yeah, that was helpful. Thank you.
Sure. All right. So yeah, I guess on that, Dragan Damjanovic, if he didn't do the work, people have cited his work in the work that they've done. So he's probably a good place to start from a search perspective along those lines. And then of course, Walter Mertz. All right, so back to the Heckman side of things. So my PhD advisor, David Payne from Illinois, used to always get excited about talking about polarizable deformable solids. And I always thought that was just a ridiculously complex phrase, but it's descriptive. So these are insulators, which means you apply an electric field and you polarize them. That's what we care about. They're insulators. They are deformable, meaning that when you apply that electric field, they're going to strain. So that could be electrostriction, which we haven't talked about yet, or it could be piezoelectricity, or both. And then solids, of course, they're solids. That's because this is an ACERS class, of course, that's what we call it. That's what we care about. So think about that. When we apply an electric field to a piezoelectric, it strains and it polarizes. But we already also know that if we change the polarization, let's say it's a ferroelectric, we change the polarization, that's affiliated with changing the temperature. But wait a minute, if I change the temperature, then that's changing the elastic modulus, that's changing how much it's straining, that's changing how much the polarization is. So you end up with this endless cycle of everything being dependent on everything else. So how do we actually know what's changing where? So as a reminder, permittivity is the change in polarization with electric field. As long as we keep the stress and the temperature constant, then we can use that partial derivative of dP dE. Compliance, so that's just inverse of stiffness. So that's how much strain we get per stress, Young's modulus, right? So again, as long as we keep the electric field and the temperature constant, then that partial derivative works out nice and easy. What about heat capacity? We never really think about heat capacity from a ferroelectric and piezoelectric perspective, but guess what? It matters. So we change entropy whenever we change the temperature. For heat capacity, that means that we're keeping stress and field constant. And so the convenient way of throwing these all together, you can do that for whatever coupled properties you feel like. And it basically means that anytime you have something that is going to respond to temperature or stress and or strain and or polarization and or field and all of these different possibilities, you can do the same thing with magnetic field. You can set up a large system of thermodynamic equations to describe what's happening. As long as you are at thermodynamic equilibrium, you can do this quantitatively. If you're not at thermodynamic equilibrium, then you can at least point and say, well, I know it's going to depend on those things, but it's really, really hard to quantify if you're not at equilibrium. Everyone hates thermo, but here it is again, back to haunt us. When we look at the free energy, so Gibbs free energy, at constant temperature, it changes, the free energy changes with stress and field, and we can rewrite those a gazillion different ways. Basically, what I want you to get out of this, and again, this is one of those slides that's really more for a future reference than anything else. Regardless of which flavor of free energy you write down, whether it's Gibbs or Helmholtz or any of the others, you can write this in terms of any set of parameters that you feel like. So as long as you're holding whatever else that is not represented here constant, then you can write these out in some way and show how they're going to relate to one another. So if you can hold the entropy constant and change temperature, or hold the strain constant and change stress and these kinds of things, then you can write out any set of these sorts of equations. What that really means is that if we're starting with this polarizable, deformable solid, we're going to say the three things that I care the most about for this example are stress and strain, electric field and polarizability, so polarization and field, and then temperature and entropy, because you just can't get away from entropy no matter what you do. And temperature is one of those things that we know that it matters for all of our properties. So I'm going to throw that one in there. If you wanted to add in magnetic field, then you can expand this further. There are many other options for expanding this. I like to keep it as simple as possible with just these three, but the concepts keep going from there. So while the equations look ugly, the parameters themselves are things that we're already familiar with. So this strain with stress, that's just compliance. This change in polarization with field, that's just permittivity. This is the heat capacity that we just talked about. And then the cross-coupled examples are, let's see, changing polarization with stress. That's, I push on a material and I get a charge. That's piezoelectricity. That's what we've been talking about. Same thing here, when I apply an electric field and get a strain. And so that's really all this is just showing how these different types of material properties and responses that we care about, how they relate to one another. And so rather than remembering equations, because I hate remembering equations, you can think about this as just a simple triangle. So you've got the electrical, and this is known as the Heckman diagram. You've got the electrical portion on one side. So the extrinsic, in this case, field is the thing that you can apply externally, and displacement. So this is like dielectric displacement or polarization. They're almost identical for now. We'll consider them essentially the exact same thing. So this is the electrical portion. So that's just electric field. and the polarization that comes out of it. We've got a thermal portion, which is temperature and entropy, and then we've got the mechanical stress and strain. And all this is doing is showing you that on the outside, you've got the things that you can change. The inside of the triangle are the responses, the direct responses of the materials. And now you can look at, well, when I change field or change the field to get a change in strain, that's the piezoelectric effect. And similarly, when I change the stress to change the displacement or affect the displacement to affect the stress, then that's also the piezoelectric effect. That's converse versus direct. And so this is just a convenient way of diagramming out how these different responses relate to one another. The useful part of this, though, is we already talked about piezoelectric being exactly the same. So the magnitude of those, even though they have different words, the coefficients and the magnitudes of those are completely identical because they're symmetric. So what about this side? We've got this thing called an electrocaloric effect, and we've also got pyroelectric. So when we talked about crystallography, I said that pyroelectricity is the amount that magnitude of the polarization in a polar material changes as you change temperature. So you have, again, we'll start with a tetragonal example. Because of thermal expansion, you're going to get a different magnitude of polarization when you change the size of the unit cell. And that change in polarization as you change temperature is pyroelectric. That's the exact same magnitude, just the opposite variables as this electrocaloric effect. So the beauty of that one is it's relatively easy to change temperature and measure a change in charge. It's really hard to change electric field and measure a change in entropy. But we know that they have to be identical because they're symmetric. And we could go through the thermo equations to show that they have to be symmetric, as long as we keep the mechanical boundary conditions the same. Another fun use of this, and we will get into this in more detail on Tuesday, but I want to show you another example of how this can be valuable. If we want to look at let's say the direct piezoelectric effect for between stress and displacement, the shortcut for that is just along this arrow. Great. Maybe for some reason I can't measure that, or maybe I can measure it and I'm trying to get at something else. But I can get between those same two, that same relationship in other directions. So if I go to the piezocaloric effect and then electrocaloric effect and then permittivity, these three combined have the exact same magnitude of value as that direct effect. So again, maybe it's easy to measure permittivity. It's easy to measure pyroelectric effect. And I've got the electrocaloric effect because I can measure pyroelectricity. And now I can calculate what the piezocaloric effect would be. Do I ever need to know what the piezocaloric effect is? Who knows? But this is a handy relationship to recognize that there are all these symmetries and different relationships that you might not have run across. For people that took physical chemistry, PChem, you probably saw these exact same kinds of thermodynamic relationships, and they were just described as Maxwell relationships. Same thing. This is just a different way of using that same thermodynamic reversibility and recognizing relationships. So we will get into this in a lot more detail on Tuesday. We will also from there jump into relaxer dielectrics, relaxer ferroelectrics, anti-ferroelectrics, and then get into even more applications of a variety of these. So PTCR and varistors and all sorts of fun things. So any final questions, please let me know. Throw something in the chat or shoot me an email. If not, then I will see everyone on Tuesday.